Parametric models are powerful because a few coefficients can summarize an economic relationship, but that strength can also become a limitation. A convenient functional form may hide curvature, asymmetry, several peaks, or other important features in the data. Non-parametric methods let the data reveal more of that shape. We begin with density estimation, where the goal is to describe an unknown distribution without assuming it is normal or belongs to a fixed parametric family. Let's be clear about what a density is. It tells us where a continuous variable is likely to land. The empirical distribution records our observations exactly, but it is a step function, so it never gives a smooth density. A histogram is more visual, yet its shape depends on where we put the bins and how wide we make them. Kernel density estimation drops the hard bins and places many small, smooth contributions on the observations instead. Add those up, and we get a continuous curve that can reveal skewness, heavy tails, or more than one cluster of probability. To build the estimator, imagine placing a small bump at every observation. The kernel determines the shape of each bump, and the bandwidth determines its horizontal scale. At a point of interest, we add the contributions from all observations and divide by the sample size and the bandwidth. The result is a local average of nearby evidence. Observations close to the evaluation point receive substantial weight, while distant observations receive little or no weight, depending on the chosen kernel. A valid density kernel integrates to 1 and is usually symmetric around 0. Symmetry means that observations equally far to the left and right receive equal treatment. Common choices include the Gaussian, Nèque-Neikov, triangular, and uniform kernels. These shapes differ in smoothness and in whether they have finite support. In most ordinary applications, choosing among sensible second-order kernels changes the estimate much less than choosing the bandwidth. That practical lesson prevents us from spending too much effort on a secondary design decision. The bandwidth controls the amount of smoothing. A small bandwidth creates narrow bumps, so the estimated density follows local fluctuations and may look noisy. A large bandwidth creates wide bumps, so the estimate becomes smoother but may erase important structure. This is the central bias and variance trade-off. Too little smoothing gives high variability, while too much smoothing introduces systematic distortion. A good estimate, therefore, requires a bandwidth that reflects both the sample size and the scale of the variable. Second-order kernels have zero first moment and a finite non-zero second moment. These moment conditions remove the leading first-order bias when the true density is smooth. Higher-order kernels can eliminate additional bias terms, but they may take negative values and become harder to interpret as probability weights. They can be useful in theory, yet they do not automatically improve finite sample performance. Smoothness of the unknown density and a sensible bandwidth remain essential regardless of the nominal order of the kernel. The Gaussian kernel gives every observation a positive weight, although that weight declines rapidly with distance. Compact support kernels, such as the H-par-Nek-Neikov or uniform kernel, give zero weight beyond a fixed scale distance. The H-par-Nek-Neikov kernel has an attractive efficiency property in a standard mean-squared error calculation. Even so, the visual difference among these kernels is often modest after bandwidths are made comparable. In applied work, robustness across bandwidth choices is usually more informative than a contest between familiar kernel shapes. The uniform kernel gives an especially transparent interpretation. Around the point where we estimate the density, draw a window whose width is determined by the bandwidth. Count how many observations fall inside that window, then divide by the sample size and the window width. As the window moves, the count changes and traces a density estimate. This resembles a moving histogram, but the window is centered on every evaluation point, rather than tied to a fixed set of bins. Comparing a uniform kernel estimate with a histogram clarifies why the two can look different. A histogram treats every observation within a bin identically and changes abruptly at each bin boundary. The kernel estimate uses a moving neighborhood, so it is not anchored to those boundaries. With a smooth kernel, the resulting curve changes smoothly as well. Neither display is automatically correct. A careful analyst checks whether major features such as asymmetry or tail thickness persist across reasonable bins and bandwidths. Daily equity returns provide a useful application because their distributions are rarely summarized well by a normal curve. A histogram of FTSE 100 returns shows the broad location and spread, while a kernel density estimate gives a smoother view of the center and tails. The purpose is not to decorate the histogram with a line. It is to investigate whether the empirical distribution is sharply peaked, asymmetric, or unusually heavy-tailed, all of which matter for risk measurement and model specification. When reading a financial return density, distinguish visual prominence from probability importance. A tall central peak means many observations are concentrated near typical values, but rare tail events may still dominate loss calculations. A small secondary bump might indicate a genuine mixture of regimes, or it might be sampling noise created by a narrow bandwidth. Kernel estimation is exploratory, not a mechanical proof of multimodality. We should compare bandwidths, inspect the raw observations, and connect apparent features to economic context before drawing conclusions. In IR, a practical workflow begins by cleaning the variable, checking missing and extreme values, and plotting both a histogram and a kernel estimate. The density function can generate evaluation points and estimated heights, while plotting tools can overlay alternative bandwidths. Always record whether returns are expressed as decimals or percentages, because a change of scale changes the numerical bandwidth. Also, avoid letting software defaults become invisible assumptions. A reported curve should be reproducible from an explicit kernel, bandwidth rule, sample period, and transformation. Transformation can help when support or scale is awkward. For a strictly positive variable, smoothing its logarithm may avoid assigning probability to negative values. Returning to the original scale then requires the transformation's Jacobian, so simply relabeling the horizontal axis is incorrect. The density target must be stated on the scale where it is estimated and interpreted. Uncertainty should accompany visual exploration. A pointwise band describes variability at one location, while a simultaneous band addresses the whole displayed curve and must be wider. Bootstrap methods can help, but resampling should preserve dependence for time series data. Even a narrow band reflects sampling uncertainty under the chosen bandwidth. It does not include every possible smoothing choice, scale transformation, measurement issue, or structural break. So let me pull this together. Kernel density estimation trades a rigid distributional assumption for a controlled kind of local averaging. The kernel says how nearby observations contribute, and the bandwidth decides what counts as nearby. Kernel choice matters, but bandwidth choice usually matters more. This can expose features that a single mean and variance would hide. Yet it cannot tell real structure from noise on its own, so we still have to bring judgment. In the next lesson, I will make that judgment systematic by studying bias, variance, consistency, and bandwidth selection. We now study why a kernel density estimator works and why its bandwidth cannot be chosen casually. At any fixed point, estimation error can be separated into a systematic component and a random component. The systematic component is bias, the difference between the expected estimate and the true density. The random component is measured by variance. Mean squared error combines squared bias and variance. This decomposition turns a visual smoothing decision into a statistical problem with explicit competing forces. The analysis requires regularity conditions on the unknown density. Continuity rules out abrupt jumps at the evaluation point, while differentiability allows a local expansion. For the standard second-order calculation, we typically need two derivatives near that point. A Lipschitz condition controls how quickly the density or one of its derivatives can change. These assumptions are not decorative technicalities. They determine which approximation is valid and how quickly the bias disappears as the bandwidth shrinks. Kernel conditions matter as well. The kernel should integrate to 1 and have controlled tails or compact support. Symmetry makes its first moment 0. A finite second moment measures the effective spread of the kernel. Together, these conditions let us express the expected estimator as a smoothed version of the true density. The smoothing is often called convolution. It averages nearby density values, which explains both the estimator's stability and its tendency to blur curvature when the bandwidth is too large. Let me build the bias intuition slowly. Instead of the raw observations, look at the expected estimate. It is really a weighted average of the true density at points close to our target. Now picture expanding that density around the target. The flat, constant part just gives the density back because the kernel integrates to 1. The next part, the one tied to the slope, cancels out because the kernel is symmetric. What survives is the leading bias, and it grows with the curvature of the density, the second moment of the kernel, and the bandwidth squared. This result gives an important interpretation. Bias is small, where the true density is nearly linear, and larger where the density has strong curvature. At a sharp peak, smoothing pulls the estimate downward because neighbouring values are lower. In a trough, smoothing can push the estimate upward. The sign therefore depends on local curvature, not merely on sample size. Shrinking the bandwidth reduces this distortion, but it also makes each estimate depend on fewer nearby observations and therefore increases variability. Higher order kernels are designed so that several lower moments vanish. Under sufficient smoothness, the leading bias can then involve a higher power of the bandwidth. That looks attractive asymptotically, but the gain has conditions. The density must possess the required derivatives, and the kernel may need negative regions. Negative weights can produce estimates that are locally negative and less intuitive. Higher order theory is valuable, yet it does not remove the need to examine finite sample behavior and economic plausibility. Here is the idea behind consistency. As the bandwidth shrinks towards 0, the kernel average draws in tighter and tighter around our target point. If the density is continuous there, and the weighted terms are bounded by an integrable envelope, dominated convergence lets us move the limit inside the averaging step. The expected estimate then settles onto the true density. That handles the bias. But consistency needs more because the random wobble must also die away. So we cannot let the bandwidth shrink too quickly because then each estimate leans on too few observations. For independent observations, the leading variance is proportional to the true density at the target and to the integrated square of the kernel. It is inversely proportional to the sample size multiplied by the bandwidth. A smaller bandwidth therefore raises variance because the effective neighborhood contains less information. A larger sample reduces variance because more observations contribute. Point-wise variance is also larger in regions where the density is high, although relative error can behave quite differently in sparse regions. Time series dependence adds covariance terms between kernel contributions from different dates. Under suitable weak dependence conditions, these terms can be controlled, and the familiar leading order often remains informative. We should not interpret that as permission to ignore dependence. Persistent returns, durations, or macroeconomic series may require assumptions and bandwidth rules adapted to serial dependence. The key condition is that the effective amount of local information grows, even while the neighborhood itself becomes narrower. Combining squared bias and variance gives the leading mean squared error for a second-order kernel. Squared bias has the order of the bandwidth to the fourth power, while variance has the order of 1 divided by the product of sample size and bandwidth. Balancing these terms gives an optimal bandwidth with the order of the sample size raised to -1/5. As the sample grows, the optimal bandwidth shrinks, but slowly enough that the effective local sample size still increases. This optimal rate is not a universal numerical bandwidth. Its constant depends on the unknown density, its curvature, and the kernel. Plug-in methods estimate those features. Rule-of-thumb methods use a reference distribution, and cross-validation selects a bandwidth through an empirical prediction or likelihood criterion. Each method can behave poorly in difficult data. A robust application compares several defensible selectors and asks whether the substantive conclusions survive, rather than presenting one automatic choice as uniquely correct. Relative mean squared error divides the ordinary error by the squared density. It reveals a problem in sparse regions. Even when absolute error is small, estimating a very small density can be imprecise in proportional terms. This matters in financial tails, where the events are rare but economically important. A visually smooth tail is not necessarily a well-estimated tail. Confidence bands, sensitivity analysis, and extreme value methods may be more appropriate when tail probabilities rather than the central distribution are the main target. Boundary bias arises when the variable has restricted support, such as a duration that cannot be negative. A symmetric kernel near 0 places weight outside the feasible region, where no observations can occur, and this can pull the estimate downward. Possible responses include transformation, reflection, boundary kernels, or local adjustment. The correct choice depends on the application. Merely trimming the plot hides the symptom without correcting the estimator. Always align the statistical method with the known support of the economic variable. Integrated error evaluates performance across the density rather than at one target point. It can weight central regions heavily because they contain more probability, even when the application cares most about rare losses. Bandwidth selection should therefore match the loss. A selector optimized for global density fit need not be optimal for estimating a tail probability or quantile. Cross-validation itself comes in two flavors. One version, least squares cross-validation, targets integrated squared error, meaning it tries to make the fitted density close to the truth in an average squared sense. The other, likelihood cross-validation, rewards a bandwidth that predicts the observations we held back. Both can jump around a lot in small samples, and sometimes they pick a bandwidth that is far too small or far too large. So look at the whole curve of the criterion near its best point, and compare neighbouring bandwidths rather than trusting one tiny numerical winner. A reliable R analysis therefore treats bandwidth selection as part of the model, not a plotting option. Inspect the data scale, choose a documented selector, compare smaller and larger bandwidths, and check boundaries and tails. When observations are dependent, preserve the time ordering in any validation scheme. Report enough information for another analyst to reproduce the curve. The central discipline is balance. Let the bandwidth fall towards 0 for low bias, but ensure that the sample size times bandwidth grows for low variance. Many economic questions concern several variables jointly rather than one variable in isolation. We may want the joint distribution of two equity returns, income and consumption, or output growth and inflation. A multivariate kernel density estimator extends the same local averaging idea. Each observation now contributes a bump in several dimensions. The estimate at a target vector is large when many observations lie nearby in the relevant joint space, and small when that combination of values is unusual. With a product kernel and one common bandwidth, distance is measured separately along each coordinate, and the coordinate weights are multiplied. The estimator is then normalized by the sample size and by the bandwidth raised to the number of dimensions. More generally, a bandwidth matrix can allow different scales, smoothing levels, and orientations. This matters because a one-unit change in an interest rate is not comparable with a one-unit change in an equity return. Standardization can help, but it does not replace thoughtful bandwidth design. The joint density contains information that separate univariate densities cannot recover. Two assets may each have symmetric marginal distributions, while their joint distribution reveals strong dependence. Extreme negative returns may occur together more often than independence would suggest. Contours of the estimated density show regions with similar probability concentration, while a three-dimensional surface displays peaks and valleys. These pictures are useful only when axes, units, and smoothing choices are clear, because visual perspective can otherwise exaggerate or conceal dependence. The bias calculation resembles the univariate case. For a symmetric second-order kernel and a smooth joint density, the leading bias is typically of second order in the bandwidth and depends on curvature across the coordinates. If a bandwidth matrix is used, curvature and smoothing interact by direction. The estimate can therefore blur a narrow ridge even while representing a broad direction well. Using one scalar bandwidth is convenient, but it may be inappropriate when the variables have unequal scales or the density has strongly directional structure. The variance reveals the central multivariate difficulty. With dimension denoted by d, the leading variance has the order of 1 divided by the product of sample size and bandwidth raised to d. Each additional variable makes a local neighborhood occupy a much smaller fraction of the full space. To keep enough observations nearby, we must smooth more aggressively or collect far more data. A sample that is large for a univariate problem can be remarkably sparse once several conditioning variables are included. For a second-order kernel, the leading squared bias still has the order of the bandwidth to the fourth power. Balancing it against multivariate variance gives an optimal bandwidth whose order is the sample size raised to an exponent. That exponent is negative, 1 divided by the sum of d and 4. The associated mean squared error deteriorates as d increases. This is the curse of dimensionality. It is a statistical shortage of local information, not a computational inconvenience that faster software can remove. The curse has a geometric explanation. Imagine dividing the range of each variable into 10 local intervals. One variable creates 10 cells. 2 variables create 100, and 5 variables create 100,000. the observations become thinly spread across those cells. Kernel neighborhoods overlap rather than forming fixed cells, but the information problem remains. To obtain the same local resolution in more dimensions, sample size must rise extremely quickly. This is why unrestricted high-dimensional smoothing is rarely a sensible default. Mitigation begins with economic structure. We can reduce dimension by selecting variables that answer the question, using factor summaries, imposing additive or single-index structure, or combining parametric and non-parametric components. Dimension reduction is not harmless, because discarded directions may contain information. The aim is to use defensible restrictions that concentrate the data where estimation matters. Regularization and machine learning can help, but their success still depends on assumptions about sparsity, smoothness, or low-dimensional structure. In finance, a joint density earns its keep in several places at once. Building portfolios, measuring how assets depend on each other, running scenarios, and gauging risk. Take a joint estimate for the FTSE 100 and the DAX. It shows how often the two markets fall together and whether their extreme moves line up along a diagonal. That is far richer than a single correlation number because the pattern can change across the distribution. Still, a smooth joint density on its own will not prove causality, dynamic dependence, or a relationship that holds steady through time. A contour plot is often easier to read than a three-dimensional surface. Closely spaced contours indicate a steep change in density, while elongated contours indicate a direction of strong association. A circular pattern suggests weaker directional dependence after accounting for scale, yet these are descriptive statements. Changing the bandwidth can join separate peaks or split one peak into several. We should compare contour maps under nearby bandwidth choices and identify whether conclusions concern the center, the tails, or both. Time variation poses another limitation. Pooling years of returns estimates an unconditional joint density that averages across calm and turbulent periods. Apparent heavy tails or multiple peaks may reflect changing volatility regimes rather than one stable distribution. A useful workflow therefore combines density plots with time plots and, where appropriate, estimates over subperiods or after volatility standardization. The goal is not to eliminate all dynamics before smoothing, but to be clear about which distribution the estimator is intended to describe. Tail dependence is particularly difficult to estimate non-parametrically. Joint extreme observations are rare by definition, so a visually smooth contour in a corner can rest on very little evidence. Report the number of observations supporting the region, compare with specialized tail methods, and avoid extrapolating a kernel surface beyond the observed combinations of returns. Bandwidth matrices can rotate as well as rescale neighborhoods. A full matrix can follow an elongated density ridge more efficiently than independent coordinate bandwidths, but it introduces more tuning parameters and numerical sensitivity. A diagonal matrix is simpler and easier to explain. The added orientation should be used only when the data can estimate it reliably. Validation in several dimensions must preserve the target. Holding out observations can compare predictive log density, but ordinary random folds break temporal ordering in dependent data. Rolling or blocked validation is safer for time series. The selected bandwidth should be assessed on an evaluation region defined before inspecting the most attractive contour plot. Implementation in R requires careful treatment of bandwidths and plotting grids. Standardize variables when scale differences are arbitrary, but retain the transformation needed to interpret results in original units. Evaluate the density on a grid fine enough for a clear surface without confusing grid resolution with statistical precision. Check that the numerical estimate integrates approximately to 1 over a sufficiently broad region. Then display contours or surfaces with consistent color scales when comparing samples, models, or time periods. Multivariate density estimation is powerful precisely because it avoids a rigid joint distribution, but that freedom is expensive. Bias depends on local curvature and the smoothing geometry. Variance grows rapidly with dimension because nearby observations become scarce. Economic structure, dimension reduction, and transparent sensitivity checks are therefore part of the method rather than optional refinements. The correct question is not how many variables software can accept. It is how many dimensions the data can support at the local resolution required by the economic problem. Let's turn to regression, but without forcing a straight line or a fixed polynomial on the data. What we still want is simple: the average value of an outcome for a given level of a regressor. This is useful when theory tells us the direction of an effect but not its exact shape, or when we expect thresholds or effects that taper off. The target has not changed. It is still the expected outcome at a given regressor value. What changes is how we estimate it, leaning on nearby observations instead of one slope for the whole sample. Consider fuel efficiency as an outcome and engine horsepower as a regressor. A linear model forces the same marginal effect at low and high horsepower. A nonparametric fit can reveal rapid changes in one range and a flatter relationship elsewhere. This flexibility is descriptive unless additional assumptions justify a causal interpretation. The fitted curve answers how average fuel efficiency varies among observed cars with different horsepower. It does not by itself isolate the effect of changing horsepower while holding every confounder fixed. The narration. Watson estimator is a kernel-weighted average of observed outcomes. At a target regressor value, observations with nearby regressor values receive large weights, while distant observations receive small weights. The weights are normalized to sum to 1. The numerator combines outcomes with proximity weights, and the denominator measures the local concentration of regressors. The estimator therefore adapts to where data are available, but it can become unstable where the denominator is small. This estimator can also be understood as local constant least squares. Around each target value, choose a constant that minimizes a kernel-weighted sum of squared residuals. The minimizing constant is exactly the narration Watson estimate. This interpretation connects nonparametric smoothing to familiar regression logic. Instead of fitting one intercept and slope globally, we repeatedly fit a local constant while moving across the regressor range. The kernel and bandwidth determine which observations count as local at every target. A regressogram is a simpler predecessor. Divide the regressor into bins and use the average outcome within each bin. Like a histogram, it changes abruptly at arbitrary boundaries. Kernel regression replaces fixed bins with moving, smoothly weighted neighborhoods. The result is usually easier to interpret as a response curve. Still, smooth appearance should not be confused with accuracy. Narrow bandwidths can reproduce random fluctuations, while wide bandwidths can make an incorrect simple shape look deceptively persuasive. Bandwidth, again, controls the bias and variance trade-off. A small bandwidth uses a tight neighborhood and can follow local curvature, but each estimate rests on relatively few observations. A large bandwidth uses more observations and is more stable, but it averages across parts of the response function that may differ. For a smooth function with one regressor and a second-order kernel, the standard optimal bandwidth has the familiar sample size rate of -1/5, though the appropriate constant depends on the design and noise. The leading bias of narration. Watson regression has two sources. One reflects curvature of the conditional mean function. The other reflects the slope of the regressor density, because local constant weighting becomes unbalanced where observations are distributed unevenly. This design bias distinguishes regression from simple density estimation. It helps explain why a curve can be distorted near rapidly changing data concentration, even when the underlying conditional mean is fairly smooth. Local linear regression is designed to reduce this problem. Variance depends on the conditional noise, the kernel, the bandwidth, and the density of the regressor. Estimates are less precise where few regressor observations occur. A confidence band should widen in those sparse regions, even if plotting software draws a smooth line throughout. Extrapolation is especially dangerous because kernel methods are supported by local observations. Outside the observed range, there may be no meaningful neighborhood at all. Non-parametric flexibility within the data does not license prediction beyond them. Boundary points create a further challenge. Near the smallest or largest observed regressor value, a symmetric neighborhood extends into a region with no data. A local constant estimator then receives weight mainly from one side and can have substantial bias. Simply choosing a wider bandwidth does not remove the asymmetry. Boundary kernels and transformations are possible, but local polynomial methods offer a particularly useful response because a local slope can adjust for the one-sided design. Local polynomial regression approximates the conditional mean near each target by a low-degree polynomial. A local linear fit uses an intercept and a slope, estimated with kernel-weighted least squares. The fitted intercept at the target is the estimated conditional mean. A local quadratic fit adds curvature. These are local approximations, not one high-degree polynomial stretched across the entire sample. Their flexibility comes from re-estimating the coefficients as the target point moves. Local linear regression has two important advantages over local constant regression. It reduces design bias in the interior, and it behaves much better near boundaries because the fitted local slope adjusts for asymmetric observations. A higher polynomial degree can reduce bias when the function is sufficiently smooth, but it also raises variance and numerical instability. In most applications, local linear or local quadratic fitting is a sensible starting point. A very high degree is rarely justified by the local data. The matrix formulation looks like weighted least squares. Construct columns for a constant and powers of the regressor's distance from the target. Build a diagonal matrix of kernel weights and solve the local normal equations. This makes implementation efficient and extends naturally to derivative estimation. In R, established smoothing functions avoid hand coding every matrix, but the analyst should still inspect local data density, bandwidth, polynomial degree, and boundary behavior. A successful calculation is not yet a credible empirical result. Cross-validation can select a bandwidth by predicting each observation without using that observation in its own fit. The bandwidth minimizing prediction error is attractive, but the criterion can be noisy and may choose an implausibly rough curve. Compare it with plug-in rules and with nearby bandwidths. Also decide whether the target is prediction, estimation of the mean curve, or estimation of a derivative, because optimal smoothing differs. The loss function should match the economic question. Derivative estimates can answer economically meaningful marginal effect questions, but differentiation magnifies noise. A bandwidth chosen for the level of the regression function is not generally optimal for its slope. Local polynomial methods estimate derivatives naturally from local coefficients, yet uncertainty should widen in sparse regions and near boundaries. Smooth-looking slopes can otherwise overstate evidence of thresholds or turning points. Causal use requires assumptions beyond flexible functional form. If treatment or exposure is confounded, a non-parametric curve estimates an association conditional on included variables, not an intervention effect. Adding controls increases dimension and local sparsity. Research design, overlap, and identification therefore remain central. A smoother can relax shape restrictions, but cannot manufacture comparable observations where the data provide none. The practical comparison is therefore not linear regression versus a method with no assumptions. Non-parametric regression replaces a global functional form with assumptions about smoothness, bandwidth, local support, and dimension. It can reveal curvature that a straight line conceals, but it needs enough observations near every reported point. Use the linear model as a benchmark. Show uncertainty and data coverage, and treat sharp features cautiously. In the next lesson, we apply these tools to predictability and volatility in financial data. Non-parametric tools are especially useful in finance because many economically important alternatives are nonlinear. Returns may be difficult to predict with a linear autoregression, yet still display sign patterns, threshold effects, or state-dependent volatility. Flexible methods can search for these features without committing to one polynomial or distribution. That freedom must be disciplined by out-of-sample evaluation and careful inference, because financial samples contain dependence, changing volatility, and many opportunities to discover patterns that do not persist. A runs test studies the sequence of signs rather than the numerical size of returns. A run is a consecutive group of observations with the same sign. For example, several positive returns followed by several negative returns form two runs. Under an appropriate null of sign independence, the number and lengths of runs have known probabilistic behavior. Too few runs can indicate persistence, while too many can indicate frequent reversal. The test is robust to some distributional features, but it discards information about magnitudes. Run length makes the same idea more explicit. At each date, record how long the current sequence of positive or negative outcomes has continued. If sign changes are independent, with a stable probability, very long sequences have predictable rarity. In financial data, however, zero returns, changing trading intensity, and structural breaks complicate the reference distribution. The analyst must state how zeros are treated and whether the sign probability is estimated. A runs calculation is a diagnostic for dependence, not a complete market efficiency test. Nonlinear Granger predictability asks whether past information about one variable improves the conditional prediction of another after the target's own history is considered. Linear Granger tests examine a particular linear conditional mean. A non-parametric approach can compare broader conditional expectations or other functionals. The phrase Granger causality is predictive, not structural. Rejection means that one information set improves forecasts under the chosen target and assumptions. It does not prove an economic mechanism or policy intervention effect. One flexible formulation applies a function to future returns and asks whether its conditional expectation depends on available information. Different functions emphasize different features. The identity function targets the conditional mean. A squared or absolute transformation targets scale and volatility. An indicator can target a tail event or sign. This perspective shows why absence of mean predictability does not imply complete unpredictability. The same information may have little value for the expected return, but substantial value for risk. A nonparametric autoregression estimates the expected current value as an unknown smooth function of past values. With one lag, it is a familiar kernel regression problem. With several lags, the regressor becomes a vector, and the curse of dimensionality appears quickly. The method can reveal threshold saturation and asymmetric responses that a linear autoregression misses. Yet, each extra lag divides the data into sparser local neighborhoods, so lag selection is a statistical decision rather than an invitation to include every available history. Weak form market efficiency is often associated with inability to earn abnormal returns from past prices alone. A nonparametric autoregression can test a broader class of conditional mean relationships than a linear model. But statistical predictability is not automatically economic profitability. Trading costs, risk, model selection, and real-time information availability all matter. A small in-sample improvement may disappear in a genuine forecast exercise. Claims about efficiency should therefore distinguish statistical rejection, forecast performance, and implementable economic value. Testing nonparametric predictability is harder than drawing a smooth curve. The null may place the model on a boundary or leave nuisance features unidentified, and observations are dependent. Resampling or asymptotic methods must preserve the relevant time series structure. Reusing the same sample to select bandwidths, lags, transformations, and test statistics can seriously distort size. A transparent analysis separates exploratory choices from confirmatory evaluation and reports sensitivity to tuning parameters rather than highlighting only the most favorable specification. Volatility offers a natural semi-parametric application. We may specify a familiar dynamic component for persistence while allowing an unknown function to capture how past shocks affect conditional variance. Alternatively, the conditional mean can remain parametric, and the variance function can be estimated flexibly. Semi-parametric structure aims to retain interpretability and statistical efficiency where theory is informative, while relaxing the part most likely to be misspecified. It is a compromise between a fully parametric volatility model and unrestricted smoothing. Suppose the conditional variance depends on a past innovation through an unknown non-negative function. Kernel or local polynomial methods can estimate that news response from squared residuals subject to positivity and enough observations across shock values. Such an estimate may reveal asymmetry, thresholds, or flattening that a standard quadratic response cannot express. The residuals are generated rather than directly observed, and their dependence affects uncertainty. Treating them as independent raw data generally produces confidence statements that are too optimistic. A sound R workflow starts with a clearly timed information set. Construct lagged predictors without leaking future values, estimate any preliminary mean model, and reserve a later period for evaluation. Standardize predictors when helpful, but preserve an interpretation in original units. Select bandwidths and lags within the training sample, then freeze the procedure before forecasting the test sample. Compare flexible methods with simple benchmarks. If a complex smoother cannot beat a historical mean or standard volatility model out of sample, its attractive shape has limited practical force. Visualization should include the raw or appropriately summarized data, the fitted function, uncertainty, and the region of adequate support. For a volatility response, plot positive and negative shocks on a common scale so asymmetry is visible. For predictability, show forecast errors over time rather than only an average score. Financial relationships can change during crises or policy shifts, so stability checks across sub-periods are essential. A single smooth curve, estimated from the entire history, may blend distinct regimes into a relationship that never existed at any one time. The most common mistake is to describe non-parametric methods as assumption-free. They assume smoothness, adequate local data, defensible bandwidths, and a stable relation over the estimation window. With time series, they also require conditions on dependence. The curse of dimensionality limits how richly we can condition. These assumptions are different from a fixed functional form, not absent. Credible work makes them visible and uses economic reasoning to decide which flexibility is worth paying for with higher uncertainty. Searching across many lag sets, bandwidths, assets, and nonlinear transformations creates a data snooping problem. The best in-sample result among hundreds of trials is biased upward, even when every candidate lacks genuine predictability. A final holdout sample, nested tuning, or a multiple model comparison procedure is needed before interpreting the winning pattern as evidence against an efficient market benchmark. The full search space should also be disclosed clearly and transparently. Across this chapter, one principle has linked density estimation, regression, and financial applications. Local averaging learns shape from nearby observations. Kernels define proximity. Bandwidths regulate detail, and dimension determines how much information is locally available. The methods can expose skewness, joint dependence, nonlinear conditional means, and flexible volatility responses. Their value comes from disciplined exploration, not decorative smoothness. Always pair the estimate with sensitivity analysis, support diagnostics, and an interpretation that respects the difference between description, prediction, and causation.